All right, today we're going to go through chapter 22, which is the transition elements and coordination compounds. All right, so the transition elements, we're talking about the D shell of when you do your electron configurations. So we have those are the transition elements, the D, where they have 10 electrons and 10 elements. Then, of course, you have your inner transition, which are your F subshell elements. All right, so when we look at our periodic table, we're talking about our transition elements. That's the ones that are here. All right, so that is 10 elements across. So that's so the first one here, when you do the electron configuration, this is going to be a noble gas and then a 4s1. This is then noble gas and 4s2. And then here is a 4s2 and then a 3d1. And then 3d2, 3d3. Okay, so it just keeps going all the way to here where you have 4s2, 3d10. All right, so the first row of transition elements, that's your 3D. All right, so this is your 3D, this is your 4D, this is your 5D, this is your 6D, but 6Ds are all man-made. We're not doing any reactions with the 6D, but we will see lots of reactions with the 3D, the 4D, and the 5D elements. All right, so the S starts at 1. For whatever reason, they left off our hydrogen or helium. So hydrogen is 1s1, and then helium is then 1s2. And then at 2, that's when we start the P's over here. This is your 2P, and this is your 3D, and this is your 4F when we do our electron configurations. All right, so your transition elements, those are the D electron configuration elements in the middle of the periodic table. All right, so they differ in main group elements in several ways. All transition elements are metals. Most have a high melting point and are hard solids. Members of group 2B are exceptions, and that, of course, is your mercury, where you'll see in 2B here, mercury, of course, is a metal, but it is a liquid metal. All right, so most have several oxidation states. There's only a couple of examples where you have elements with only one oxidation state. That's in 3B and 2B. All right, compounds of transition elements are often colored. All right, so they are paramagnetic, very colorful compounds. All right, so here are 4 oxidation states of vanadium. All right, so if you calculate the oxidation state, you will get a +5 here because oxygen is -2, so that's -6. This has to be a +5 in order to give an overall -1. This is your +4 oxidation. Again, oxygen's -2. The vanadium has to be +4 in order to give an overall charge of +2. Vanadium +3 in solution is +3. Vanadium +2 in solution is +2. And note the different colors for the different oxidation states of your vanadium. All right, so we went through the electron configurations. Here it is. Argon is the noble gas core, and so the first one is the 4s2 3d1. Note that they will always write the electron configuration in number order. The 3d1 would come first, and then the 4s2. And this is very helpful when you're making the getting the electron configuration of, say, titanium +2. You would take the 2 4s electrons off first. All right, you always take the electrons out of the highest energy principal quantum number, which in this case is a 4. All right, so that is just showing the high melting points. You got melting points of, 1,000. Yeah, so then again, now when you get to the zinc, Now that's only at 420, so that is much lower. And then you go down that column and you get to mercury, and it's actually a liquid at room temperature. All right, covalent radii. So things that are similar in size will react very similarly. And so as you go down the periodic table, you get larger and larger and larger. All right. However, when we have our 3D, note period 4 is the 3D. All right. And so then we go from 3D to period 5, which is the 4D. So the 4D elements. And then you have the period 6, which is the 5D elements. And we notice that the covalent radii of the elements in the 4D and the elements in the 3D are very, very similar in size. All right, so we have a plot here, and so the period 4, again, that's our 3D. This is period 4, which is our 3D. All right, so if you look at, say, a cobalt, all right, so its covalent radii, whatever, you can read it off of here, it's about 115 or so. All right, so you have, then you go to rhodium, all right, which is up to 125. All right, so that went up by like 10. So here it only goes up a slight amount when you go to iridium, which is say 127 or so. All right, so they are very similar in size. They are the same size when you are here. They're exactly the same size, and here they're pretty darn close. Here they're so close they couldn't only make one dot. All right, so they're a little bit different here and here, but again, same here, and just a tiny difference here. All right, so they are not larger like when you see period 4 to period 5. All of the period 5 are larger than the period 4. But when you go from 5 to 6, they're very similar. And the reason is when you're going from 5 to 6, you are filling the 4F subshell. That is the difference. All right, and so the first 4F electron is lanthanum. So this is called the lanthanide contraction. All right, so between lanthanum and hafnium in period 6, there are 14 inner transition elements filling the 4F subshell. By the time the 4F subshell is filled, the radius of period 6 transition elements is similar to that of period 5 elements. All right, so that is just called the lanthanide contraction. Right, and so now period 5 and 6 are about the same size, and you will notice that they react very similarly. They have very similar properties. All right, so your period 5 and 6 have very similar properties, different than the period 4 transition elements. All right, your ionization energy for the 4th period transition elements vary irregularly. Okay, so they tend to increase from left to right. The other rows also behave that way, so there's not a perfect periodic trend, but they tend to increase from left to right. Note that all the 6th period elements have, after lanthanum, have ionization energies higher than those of the 4th and the 5th period transition elements in the same group. All right, so your oxidation state. So we just did the electron configurations of the first row of Ds. We had the 4s2, 3d1, and then we have the 4s2, 3d2, and et cetera, all the way to 4s2, 3d10. All right, and so again, when you're removing the electrons to get positive metals, metals will have positive oxidation numbers, you're going to remove the 4s electrons first. So most of your transition elements have a stable +2 oxidation state because you have 2 electrons in the higher energy 4s, or the next one down, 5s, or the next one down, 6s. So all of them have an S2 that are easily removed. All right, and so you have a +2 oxidation state for all of them except for scandium, which only has a +3 oxidation. And +3 is also very, very common to lose the 3 electrons. So all of them are, not all of them, again, there's going to be 9 out of 10 that have a +2 oxidation. There's also going to be 9 out of 10 that have a stable +3 oxidation state. All right, and so if we look at it here, we see that our +2, the only one missing a +2 is scandium right there. The only one missing a +3 is zinc right here. All right, and also note that when you do your electron configuration here, you have a 4s2 3d1. So the maximum oxidation that you can get is a +3. You lose all 3 of your valence electrons. So titanium, that it would be a +4 if it lost them all. Vanadium, it would be a +5 if it lost them all. Chromium, it would be a +6 if they lost them all. Manganese, you'd have a +7. And note, you can barely tell on the slide here, but the common oxidation states are bold. All right, and so what I just circled are the maximum oxidation numbers for those elements, and they are all bold phase. They are all stable oxidations of that metal. All right, and so now we get to iron. Well, iron would have 8 because it has a 4s2 3d6. All right, but it does not remove all 8 of them. All right, it is not known to have a +7 or a +8 oxidation state. Its highest is a +6. The maximum for iron would be predicted to be 8. We don't get that high. All right, but you do get the maximum oxidation numbers for the first 5D elements. All right, again, the maximum is when you lose all of your electrons past the noble gas core. All right, so again, 9 out of 10 have a +2 oxidation, 9 out of 10 have a +3 oxidation, the two most common oxidation numbers. Now, +4 is then next, where you have 7 of the 10 have a +4 oxidation that is stable. Well, +2 and +3 are common oxidation numbers. A note here, only scandium with a +3, it only has one stable oxidation number, and zinc at a +2 only has one stable oxidation number. When we memorized our oxidation numbers, we had nickel is always a +2, but there are other stable oxidations of nickel. It can become +1, +3, and +4 as well. Copper we memorized as cuprous and cupric as a +1 and a +2. You can also get copper to be a +3 oxidation. Same here with your iron. The bold ones are the 2 and the 3 because those are the common ones, but you can also get a 4, a 5, and a 6. All right, so chromium, again, you have your transition elements make colorful compounds due to your paramagnetic electron transferring in the d orbitals. All right, you got stable oxidations of +2, +3, and +6. So they are colorful, and the word comes chroma, means color. All right, so there's just a couple of pictures of your chromium. And all right, and so 2 very common chromiums, and we use the dichromate, is the sodium chromate, that is yellow, and the sodium dichromate, which is orange. This is what we used in our oxidation reduction titration. That was our orange solid. And you can convert the sodium chromate to the dichromate by treating it with acid, which they show here. So if you have your chromate, which is yellow, you add your acid, and this will turn an orange dichromate color. All right, and the dichromate, again, we used it in our oxidation reduction titration because it is a very strong oxidizing agent. It has a very large E naught value of 1.33 volts for its reduction potential. All right, so copper. So we have copper as, we have it memorized from first semester as a copper +1 or a copper +2. But we saw in the previous slides that it can also be a +3. but the most common, +1 and +2. All right, so you have copper. If you have a penny, a pure copper penny, one that's older than 1981, and you add nitric acid, the nitric acid will oxidize your copper to a copper +2. And so your nitric acid is an oxidizing agent. All right. And so you have the result of a copper +2 in water is going to form this complex. And the complex of Cu H2O sub 6 +2 is called hexa aqua. And whether you put hexa aqua or hex aqua, which is the way you should, only you shouldn't put two A's together here. But I will, either way is fine. Hexa aqua, 6 waters, copper 2. All right, now the reason why we know it's copper 2 is we can draw the Lewis structure of water. All right, so back in chapter 10, Lewis structures, very important to know how to do Lewis structures. And also in chapter 18, when we did our complex ion formations, you have a Lewis base. So a Lewis base is an electron pair donor. And so your Lewis acid is your copper +2. And so you have your electron pair going to your copper +2. We have that happening 6 times. And so we have a coordinate covalent bond. So we remember the coordinate covalent bond means that both electrons come from the same atom. And so the oxygen, both electrons came from the oxygen to form that bond. And that is the only difference between a coordinate covalent bond and a regular covalent bond. A regular covalent bond, 1 electron comes from each of the atoms. All right, and so this is going to happen 6 times. And so we have a coordination number of 6. All right, so your coordination number is 6. Anytime your coordination number is 6, you are octahedral. And when you are octahedral, you are sp3d2 or d2sp3. You have to have 6 orbitals for the 6 coordination sites for your ligands to come in. Now, all right, so water is a Lewis base. All right, that's because it's an electron pair donor. And then your copper is the Lewis acid. It is the electron pair acceptor. Once the water is on the metal, it is no longer called a Lewis base. It is called a ligand. And so once you are on the metal, now you are a ligand. As it's reacting, it's a Lewis acid, Lewis base reaction. Once your Lewis base is on the metal, we now call it a ligand. All right, so we can test for a reducing sugar by putting our reducing sugar into a copper +2 solution. So we have this blue, and anytime you have a blue solution and they say there's an element, a metal in there, you would predict that to be a copper. Very common to have copper +2 solutions be a blue color. All right, and so we're going to add a reducing sugar. So that is, say, glucose. Glucose is an aldose. All right, and so what's going to happen is my aldose is going to be oxidized into a carboxylic acid. All right, and so now instead of an aldehyde, I have a carboxylic acid. And what happens to the copper? Well, the copper goes to copper +1. And in the red, it's a copper 1 oxide, which is a brick red precipitate. And so you get Cu2O, which is a copper +1 oxidation. All right, and so this is your sugar here. It is a reducing sugar because when we added the sugar, it reduced the copper +2 to a copper +1. So a reducing sugar just means it is a reducing agent, and it happens to be a sugar that we're using, and so it's called a reducing sugar. And so you reduce the copper to copper plus 1. You oxidize the sugar from an aldehyde to a carboxylic acid. You have 1 oxygen to this carbon here. You have 2 oxygens to this carbon over here. Add oxygen is oxidation. That is the definition for organic and biochem. All right. Complex ions and coordination compounds. So we have 2 different complexes here. One is an iron with 6 waters. So again, this is hexa aqua, or simply hex aqua. Should only be 1A, but I'll take 2 A's, that's fine. Hexa aqua, and then iron 2. All right, and so we know it's 2 because water is neutral. No charge for water. The overall is plus 2. That means the iron has to be plus 2. All right, when we do the Lewis structure of Cn, when we do our FeCN6 minus 4 ion, all right, so we have to do the Lewis structure of Cn. And here is the Lewis structure of Cn, where both the C and the N both have an octet. Nitrogen is just as you would predict, 3 bonds in an electron pair. Carbon is not. Carbon is supposed to have 4 bonds. This carbon only has 3 bonds and a lone pair, 1 electron pair. All right, and so when you look at your formal charge with your covalent bonds here, 1 electron came from each of the atoms. All right, and so if you look at nitrogen on the periodic table, it's in your column 5. It brought in its 5 valence electrons. Carbon is in column 4. It should have brought in 4 valence electrons, and here we show that it brought in 5. You have an extra electron on that carbon, and it is a negative charge. And so you have not neutral here, but you have minus 6. When you have 6 CNs, that's a total of minus 6. The overall is minus 4, and so your iron here is a plus 2. And so now we have hexa cyano, and note this is cyanide, and we will see on a slide your IDE is going to go to O when you are a ligand. So a ligand name is going to be cyano. A Lewis base name is cyanide. So this is the Lewis base. So if you're naming the Lewis base, it is cyanide. If you're naming the ligand, it is cyano. All right, so hexacyano. And now another rule when you're naming stuff is you have your negative. When it is negative, the metal ends in ATE. So being a negative charge overall, now my metal name ends in ATE. All right, and so it is ferrate. All right, but if you call it ironate, I am fine with that. All right, ironate is acceptable. It is not correct, but the key is I need you to know it has to end in ATE. Ironate 2, but it is actually ferrate. All right, so ironate or ferrate 2 is the name of that. Hexacyano ironate or ferrate 2. Always the oxidation of the metal has to be given in the name with Roman numerals. All right, so some transition metals have biological activity. So you have all of these different elements, and you'll look at your vitamins and minerals, and you'll see that a lot of these things are in there, and they have benefits to the body. That's not going to be on the test, but interesting to see. All right, your complex ion. All right, so this is your metal with Lewis bases. Again, once the Lewis bases are attached to the metal, they are then called ligands. All right, so it can be an ion, which means it has a charge, a plus charge, a negative charge, or if it is neutral, it's just simply called a complex. All right, so that would be then a neutral. So a complex ion, whether it's plus or minus charge, it's a complex ion. If it's neutral, it's just simply called a complex, not an ion. All right, so your coordination number, again, is the number of coordinate covalent bonds. It is the number of bites into the metal. All right, so here you have 2 ligands. Here you have iodo 3 times. Coordination is 3. Here you have 4 chloros or 4 COs. Again, coordination number is 4. When your coordination number is 4, we're going to do a lot of 4s and a lot of 6s. The 4 is either going to be square planar or it's going to be tetrahedral. All right, if you have, again, coordination number of 5 things attached, here is coordination number of 6. 6 is the other most common. It is the most common. It is octahedral. 7 is rare. 8 is rare. So these are very rare. All right, so you've got your pentagonal bipyramidal and you got your square antiprismatic. You don't need to know that. Those are very rare. All right, a monodentate ligand. So this is the one that takes one bite, one connection. That's the ones we've seen so far. That's your CN. All right, and so the metal, it goes right here. So it is one coordinate covalent bond. H2O, same thing. 1 NH3, same thing. 1, 3. You can have some that take more than one bite, and those are called, if it's 2 bites, 2 coordinations, it is called a bidentate. Ethylene diamine is a very, very, very common ligand, and it is a bidentate ligand. So ethylene diamine, ethylene is CH2, CH2. So CH2 to CH2. Diamine, which means you have an NH2 and you have another NH2. So that is ethylene, 2 carbons, diamine, nitrogen, NH2 groups, and these nitrogens each have an electron pair, and so it will coordinate to the metal not in one spot, but in both diamines. Both amines coordinate to the metal. So 1 ethylene diamine is a coordination number of 2. So it has 2 coordinate covalent bonds formed for the 1 ethylene diamine. That's why it's called a bidentate ligand. All right, and so we're going to see that we're going to have a cobalt 3 that's going to have 3 ethylene diamines, and that means the coordination number is going to be 6 because each ethylene diamine is 2. All right, and so here is our cobalt ethylene diamine sub 3 plus 3. So let's name it. So ethylene diamine was a neutral molecule. All right, and so 0 for the charge of ethylene diamine. So that means your cobalt has to be a plus 3 to give an overall of plus 3. Now, the name is ethylene diamine. Anytime you have a ligand name that has the Greek prefix, you cannot use another Greek prefix. And so to say that you have 3 of these ethylene diamines, you don't use tri, you use tris. So this is a tris ethylene diamine cobalt 3. And again, it's not cobaltate because it's not part of the anion, it is part of the cation. So if it is neutral or part of a cation, it is simply the name of the metal, which is cobalt, and you always give the oxidation number, which is 3. All right, so here they show all of the bonds, even the hydrogen bonds. All right, but the shorthand is we are concerned, our concern is the coordination number. So we know that a nitrogen is coordinated here, and then there's some carbons attached, and then another nitrogen is coordinated here. So the shorthand way to write it is fine. You can write it either way, but it is fine to write it in the shorthand way, or you can write out all the carbons, nitrogens, hydrogens. Either way is fine. All right, hemoglobin has a coordination number of 4, so it is a quadradentate ligand. Quad is 4 spots that it will bind to the metal. Let's see, so yeah, the hemoglobin consists of your iron, which again is bonded to the iron in 4 coordination sites. All right, when we do EDTA, and we did the experiment EDTA, ethylene diamine tetraacetic acid, or tetraacetate, because we put it in pH 10 and removed all of the H's. And we see that this has a coordination number of 6. 1, EDTA, has a coordination number of 6. And so every time EDTA is on a metal, it is going to be octahedral, because EDTA is going to have a coordination number of 6, which is the number for octahedral. All right, and so here you've got your heme, you've got your iron bonded to 1, 2, 3, and 4 spots. All right, and so this is actually in a square planar arrangement. They are showing these bonds being a 90-degree bond angle. Your EDTA, this one is harder to see this as an octahedral, but there are 6 coordination sites here, and it is an octahedral conformation. All right, and so you have your 2 oxygens. The red are the oxygens. The one has the double bond. It is neutral. The one with the single bond is negative. The one with the single bond is negative. The one with the single bond is negative. All right, so it's coordinated through all the 4 negative oxygens, and it's also connected through the electron pair of each of these nitrogens. So the 6 coordination sites, 4 from the oxygen that has a negative charge, and 2 from the nitrogen's electron pairs. And that's how you get your 6 coordination sites. All right, so ethylene diamine, of course, is then a polydentate ligand. More than one bite into the metal. And when you form this, it forms a cyclic compound, and so it is called a chelate. And so any ligand that has more than one connection is called a chelating ligand, all right, forming a ring. All right, EDTA, if you read labels of foods, you got hair, lots of different conditioners, shampoos. Many times you will see EDTA listed as ingredients. All right, so history, we found a bunch of compounds in the 1700s where we had cobalt with chlorine and NH3. We also found a lot of platinum with chlorine and NH3. They were composed of 2 stable compounds. They were called complex compounds or just complexes. All right, so you have oxidation. A lot of these complexes are easily oxidized in air. You work with these things in a glove box, and you put your hands in this box, and it's a nitrogen or an argon atmosphere, so it's not reacting with oxygen from the air to oxidize it. So they call those compounds air sensitive because they will oxidize in air. All right, so in order to find, so they would know that it has 4 chlorines and 6 ammonia groups, but to find out what the actual composition, the actual structure of this, they did a test for the I value, so the number of ions in solution. All right, so that's your I value. We use this when you did freezing point depression, boiling point elevation, your osmotic pressure. All right, so we had the I in the equation, the number of ions in solution. All right, and so back in the day, they just labeled it like this. All right, and so now we did a reaction, we did a experiment to find out how many ions we had in solution. And so when it was calculated to be 5, there was only one way to get 5 ions in solution. and that was to make all 4 of these chloride ions plus the 1 platinum ion. And so when you break this up, you put it in water, and you get a platinum NH3 sub 6 plus 4 and 4 Cl minuses. And so you have the 4 Cl minuses for 4 ions in solution plus the platinum NH3 sub 6 plus 4, another ion in solution, and that's how you get 5. Same thing here. This is going to be your platinum NH3 sub 4 Cl2. That's going to have a plus 2, and then you're going to have 2 Cl minuses. So you have your platinum plus 2 complex, and you have your 2 Cl minuses. That's how you get 3 ions in solution. 2 ions in solution, this is just going to be a plus 1, and that's going to be a minus 1, and that is your 2. This is a neutral complex having 0 ions in solution, just the 1 molecule, but no ions in solution. Remember, when we're doing our calculation, if we have no ions in solution, it is ions in solution or molecules. When we're putting in the I value here, it is going to be put in as a 1. But number of ions, there are no ions. It's a neutral complex. All right, now to name them, all right, so the first one is going to be named hexamine. Again, you have 2 A's together. So you have hexamine. So whether you put 2 A's or 1 A, I don't care. It is hexamine. And now platinum 4. And then chloride. Now, why not chloro? Well, because the Cl is not a ligand. If the Cl is a ligand, then it's chloro. If it is not a ligand, then it's just like NaCl, sodium chloride. It is chloride. All right. Now here we have a tetraamine. And note the spelling of amine with 2 M's. It's not amine like an organic functional group amine. It is amine for ammonia. It is just an abbreviation. That's the ligand name for ammonia. Again, still platinum 4. We still have the 4 Cl's, so this is still platinum 4. But I didn't put the dichloro. Dichloro. All right, so you have your tetraamine dichloro platinum 4 chloride. So now I wrote chloro because 2 of them are ligands, and then I wrote chloride. So you have to be thinking, why did I write dichloro here and not dichloride there? Well, because this is a ionic compound with a plus and a minus. And so if you're naming NaCl, that is not sodium monochloride, that's simply sodium chloride. All right, versus if you're naming the compound CO, that's not called carbon oxide. No, because there's carbon monoxide, this is carbon monoxide. All right, so when you are naming your ionic compounds, you do not use the Greek prefixes. So you just say chloride, not tetrachloride. It is simply just chloride, not dichloride, just chloride. And so you have to give the oxidation of the metal. And so when you write that compound, you easily know how many chlorines are required. And so this one here, you got your triamine, trichloro, and platinum 4 again. And chloride. And then the last one is simply your diamine, tetrachloro, platinum 4. So all of these have 4 chlorines for a minus 4. All right, but we didn't do the Lewis structure of that. So why is chlorine minus 1? When you draw the Lewis structure of Chlorine, you have Cl and you have 8 electrons around that chlorine to give it an octet. Chlorine should have 7 electrons. It has 8. It has a negative charge. NH3, why is that neutral? Well, because NH3 looks like it should. All your nitrogens should have 3 bonds and electron pair. That's what it has. It is a neutral molecule. All right, so we did some naming. Here's the rules. So when you're naming coordination compounds, the cation name precedes the anion name. So you want sodium chloride. It's not chloride sodium. It's the positive ion is always named first, then the negative ion next. The complex name consists of 2 parts written as one word. All right, so you've got your ligands and then you got your metal. All right, so whether it's an anion, a cation, or neutral. All right, the ligand name named using a Greek prefix. So that's our dichloro, that's our tetraamine. So we use the Greek prefixes for the number of ligands. The complete metal name consists of the metal named with the suffix ate if it is part of the anion. If it is neutral or it is positive, you simply give the metal name. Only if it is part of the anion will the metal name end in ate. All right, so you will notice that your ides always go to O. So if you have bromide as a Lewis base, it's a ligand, it's bromo. All right, all of the ides, negative, all of the ides go to O. Every single IDE is going to O. All right, now, so that's, you could say IDE, and we're going to convert that as a ligand to an O. So you change your IDE ending to an O ending. All right, but if you have an 8 ending, like carbonate, sulfate, any of the 8s, permanganate, any ATE, you drop the E and you add an O. All right, so you don't drop the ATE, you simply drop the E and you add O. For the ide, you drop the entire IDE and you add O. For the 8, you only drop the E and add O. So this is carbonate O. This is oxalate O. This is sulfate O. You're just dropping the E of the 8 and changing it to an O. All right, so the neutral ligands, you would just name the molecule. So if you have carbon dioxide, it would be just called carbon dioxide. All right, except for 3 of them, and it's these 3. So water as a ligand is not water. It's not hexawater. It is hexaaqua. So you have to know that if you are naming water as a ligand, it is aqua. Again, it's not hexacarbon monoxide. It is hexacarbonyl. So you have to know that your carbon monoxide is named as a carbonyl when it is a ligand. And your ammonia, we already did this one a bunch of times, is amine. Note it is not the functional group for organic amine, which is just 1 M. This is amine with 2 M's because it is referring to ammonia as a ligand. All right, so we already know our Greek prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. All right, again, if you've already used a Greek prefix in the ligand name and you have more than one of those ligands, then you would use the alternate prefixes: bis for 2 of them, tris for 3 of them, tetrakis, pentakis for 5. All right, so if you've already used the Greek prefixes, you're not going to have a di, whatever. You're going to have a bis, di, whatever. So once you've used the Greek prefix, if the ligand name has a Greek prefix in it and you have more than one of them, you have to use the bis, tris, tetrakis, or pentakis name. All right, so again, if you're part of the anion, we did iron. Again, I would accept ironate. Ironate would be acceptable, but that is ferrate. Copper, I would again accept copperate, but it is cuprate. Gold is aurate. All right, so again, Why is gold, you look at the periodic table, it's Au? Well, it's because it's from the Latin name aurum, and so it's aurate as a negative part of the anion. Iron is on the periodic table Fe because it is from the Latin name ferrum, and that would be then ferrate. And then you have your ferrous and your ferric. You have your cupric, you have your cuprous and your cupric for your copper. So lead, we didn't do the +2 and the +4 for that, but that is plumbus and plumbic. And so that is Pb on the periodic table. So that's from the Latin word plumbum. So that's plumbate. And then silver is Ag, argentum. So that as a negative ion would be argentate. Argentate, yeah. So, but again, silver 8 I will accept. So 10 is Sn because it's from stannum, and that's stannate. Again, I would accept if you're naming it and you don't know it's the 10 is stannum and it's stannate. Fine, I will take 10-8 as the answer. All right, so we've already named this first one. We'll name it again. So in A, you've got your tetraamine. Again, I didn't go through this though. You put it in alphabetical order. Amine is A and chloro is C. So again, it's not about the how many of them. It's not the tetra and the di. The Greek prefixes do not count for alphabetical order. It is amine versus chloro, dichloro. And now again, we have 4 chlorines. So this is a -2. This is a -2 because each chlorine is -1. The NH3s are neutral. So this is a platinum 4. And then chloride. All right, and so the next one is neutral. So the first one was so if you did it, this was a +2, and this was 2Cl minus. This I value is equal to 3. Here, there's no ions in solution, but I is also molecules in solution, so that would just be the molecule stays together, no ions. So this is your diamine, dichloro, platinum 2, because now you only have 2 Cl, so that's a -2. You got 2 NH3s, that's neutral, so the platinum had to be a +2. All right, so in C, that's a new one here. We got potassium. And then we have hexa, chloro, and then platinum. Now we need the oxidation, but it's not going to be platinum once we see that this is a 2K plus, and this is a platinum Cl6 -2. So our I value here is 3, and we see that the platinum is part of the anion, and so it is platinate. It has to end in ATE. If you want to say platinumate, platinate, it has to end in ATE, and it has to be plat. So it is a platinate. All right, so you have, then you need the oxidation number. So potassium is +2. There's 2 of them, that's +2. Chlorine is -1, so that's -6. And so for that to be a neutral compound, your platinum has to be a +4. So that is potassium, not dipotassium. These are positive ions. These are ionic compounds. Potassium, hexachloroplatinate 4. All right, so now we have a hexa aqua. So they do put the 2 A's together. Looks a little weird, but fine. Hexa aqua, iron 2 chloride. All right, so you have your iron with H2O sub 6, and then you have Cl. But you are given, always must be given, the oxidation number has to be given whenever you give the name. So what do we know? We know that iron is +2. They tell us that in the name. The name tells you the oxidation of your metal. Water, we draw the Lewis structure of water. We see that it is neutral. Water is a neutral molecule. And this is a compound, which means it is going to be neutral, which means we have to have a -2, which means we have to have 2 Cl's. And so this could be give the structural formula. This could be give the I value. So the I value is 3. You have 2 Cl minuses, and you have an FeH2O sub 6 plus 2. So this would be a plus 2, and you would have 2 Cl minuses. That's how you get an I value of 3. All right, structure and isomerism and coordination complexes. So 3 properties of complexes, pivotal in better understanding coordination compounds. Isomerism, compounds having the same molecular formula but different arrangement of your atoms, just like we did with our butane and isobutane. They are isomers. Paramagnetism, so very common to have a unpaired electron when you have your transition elements. And so the electrons moving from one d orbital to another d orbital is right in the electrochemical spectrum in the color region, the visible region of your spectrum. And so these compounds are usually very colorful. All right, so constitutional isomers, structural isomers, these are called structural isomers. So constitutional or structural isomers, that's the same thing. So they differ in how the atoms are arranged together. All right, so that's a butane versus an isobutane. Those are structural isomers. When you're looking at stereoisomers, now you're looking at cis-2-butene, trans-2-butene. All right, so these are isomers in which the atoms are bonded in the same order, but different in their precise arrangement of atoms in space. So that is a cis and a trans. That is a D and an L. If we looked at an amino acid, a D amino acid, an L amino acid. It's just a mirror image, but they're not the same. All right, those would be, both of those would be stereo isomers. All right, and so we're going to look at 2 kinds, cis-trans. These are also called geometric isomers. And they're also called diastereomers. They are not mirror images, not superimposable. And then we're going to look at our, say, our L amino acid versus our D amino acid. All right, these are mirror images that are not superimposable. And that is called enantiomers. And note, cis and trans, diastereomers, these are not mirror images. If you take the mirror image of cis, it's cis. You take the mirror image of trans, it's trans. All right, so they are not mirror images. Your D and L, if you have your L amino acid and you take the mirror image, you have the D amino acid. That, again, those are mirror images. Those are not the same. Those are called enantiomers. So all of these things are your stereo isomers. All right, so we're going to look mostly at cis and trans. All right, so we have our diamine dichloroplatinum 2. All right, so this is known to have 2 isomers. When we look at this, we see that we have a 2 plus a 2. Our coordination number is equal to 4. When your coordination number is equal to 4, you're either going to be square planar, and in square planar, you have cis-trans. Possible. Or it's tetrahedral. When you are tetrahedral, you have LD isomers possible, but only if you have 4 different groups to that metal. So the metal has 4 bonds. It would have to have 4 different groups to it. You would have to have 4 different ligands attached to the metal. All right, and so we see that we do not have 4 different ligands attached to the metal. We have 2 NH3s, we have 2 CLs. All right, and so then, since it tells us we have 2 isomers, then we know we are square planar. And so you will have your platinum, and then you can put your CLs 180 degrees apart, which is then called the trans isomer, when they are 180 degrees apart. Or you can put them 90 degrees apart in a square planar, and that is cis. And so you have your cis and your trans. So when you do square planar, trans is when they are 180 degrees apart. Cis is when they are 90 degrees apart. This is a square planar. That's 90. That's 90. That's 90. It is a square. They are 90-degree bond angles. It is square planar. So when you have 2 groups that are 90 degrees away from each other, that is the cis isomer. When they are 180 degrees away, that is the trans isomer. All right. If it were tetrahedral and you had a metal, you would have to have 4 different groups to have a mirror image that is not superimposable. And so these are exactly the same. You take the mirror image. The only way they're different is if you have 4 different groups on the metal. That means 4 different ligands attached to the metal. Then you would have a D and an L situation. You would have a mirror image that is not the same. You would have enantiomers at that point. All right, so square planar. So here they show it again. You got your cis, where the 2 chlorines are cis. And you got your trans, the 2 chlorines are trans. Again, cis is 90 degrees and trans is 180 degrees. They are different compounds. You will have, so in this case, your cis platinum is an orange yellow and your trans platinum is a pale yellow. All right, if your coordination number is 6, there's only one choice, and that's octahedral. So when you have a coordination number of 4, that's when you have your choice of square planar or tetrahedral. When it is a coordination of 6, it is always an octahedral. And so if we look here at the cobalt, we got 4 NH3s, we've got 2 CLs, we have a coordination number equal to 6. We know that is octahedral. So when you draw your octahedral looks like this. And we can draw it 2 ways. One way is when you put your CLs 90 degrees away from one another. And then you have your NH3, your NH3, your NH3, your NH3. Or you could put your CLs 180 degrees away from one another, and you have your NH3, 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 NH3. So when your CLs are then 90 degrees away, that is your cis isomer. And when they are 180 degrees away, this is the trans isomer. So you can have cis and trans for square planar. You can also have cis and trans for your octahedral. 90 degrees away versus 180 degrees away. All right, so again, here is where your chlorines are 90 degrees apart, and here's where your chlorines are 180 degrees apart for your cis and trans complex. All right, and then this one is even more obvious that they are completely different because you have a purple solid versus a green solid. The cis is purple and the trans is a green solid. All right, are there any geometric isomers for this complex? Anytime you have 2 of the same thing here, they can be 90 degrees apart or they can be 180 degrees apart. So the answer is yes, you have cis and trans. It's exactly the same as the last picture we draw, but instead of drawing CLs, you would draw NO2s. And so instead of having the CLs here, we have NO2s that are 90 degrees away for cis and 180 degrees away for trans. All right, so when we have 4 different ligands on a coordination number of 4, and it is a tetrahedral, then we can have optical isomers or enantiomers. All right, so it must be tetrahedral for us to have a normal enantiomer. This also works for the octahedrals. I'm not going to put any octahedral enantiomers on the test. I will put tetrahedral enantiomers on the test. All right, and so it's just a non-superimposable mirror image. Right, so that is just like your right hand differs from its mirror image of your left hand. If you don't believe it, go find a left-hander and say, I want to borrow your glove, and the glove's on the wrong hand. If you find a left-handed batter and say you want to borrow his bat and you're right-handed, it doesn't matter. So a glove is chiral. It's a chiral object. A bat is an achiral object. Doesn't matter if you're left-handed or right-handed, you can use a bat. A golf club is chiral. If you're left-handed and somebody gives you a right-handed club, it doesn't do you a whole lot of good. All right, and so you have chiral objects. If it has a left hand and a right hand, then it is a chiral object. When we have a chiral compound, what we're looking for is the mirror image not being exactly the same, not superimposable. All right, so this would be a very difficult question, one that people will go too fast and get the wrong answer. And I would say, what's the coordination number? And you'd say 2, and you would say 2, and you would say 4, and it would be wrong. Make sure you're looking at the ligands. You have to know that En is ethylene diamine. This is a bidentate ligand, and so the coordination number here is each one of these is 2, so that's 4. Coordination number here is 2. So the chlorine, there's 2 of them, 1 bite each. Ethylene diamine, 2 bites each. This has a coordination number equal to 6. This is octahedral. All right. And so, again, you would have the chlorines that could be 90 degrees away. That would be your cis. You would have the chlorines that would be 180 degrees away. That would be your trans. But now, not only are we drawing the trans where they are 180 degrees away and our cis, which are 90 degrees away, we are also giving the mirror image of this molecule. And for the trans, the mirror image is exactly the same. But for the cis, since you have these linkages do not line up correctly when you take the mirror image of your cis. And so the cis has 2 enantiomers. And so you have your 3 stereoisomers. You have trans and you have cis number 1 and cis number 2. I am not going to put octahedral ones on the test, but the test you need to know. How do you test for enantiomers? You take the mirror image and you see if it's exactly the same. If it is not the same, then it is optically active and an enantiomer. All right, so again, yes, enantiomers. The interesting part is they differ only by the direction they rotate the plane of polarized light. All right, so they have identical melting points, solubilities, colors. They are all exactly the same, except when you put it in a polarimeter, one will rotate the plane of polarized light in the clockwise position, which is a lowercase d, which is dextrorotatory. This is not capital D. This is lowercase d. This is something you take it into the lab, you stick it in a machine, and it rotates the plane of polarized light in the clockwise direction. If it rotates the plane of polarized light in the counterclockwise position, then it is levorotatory, and it is a lowercase l. This is not capital D and capital L. Lowercase d, lowercase l. In order to find the D and the L, you have to go to the lab, and you have to put it in a polarimeter. It is an experimental information here. The capital D, the capital L, that is just a name, a convention. That's how we name our different compounds. It is not anything that is done in the lab. In order to find if it is dextrorotatory or levorotatory, you must do that by experiment. All right, if you have equal amounts of your enantiomers, so your enantiomers, so if one rotates it 20 degrees clockwise, the other one would be 20 degrees counterclockwise. So if you had the clockwise one and it was 20 degrees clockwise, and then you put in the other enantiomer, it would be minus or counterclockwise, which I'd call minus counterclockwise. All right, so the plus or D, this is a lowercase d. So the plus indicates clockwise, D indicates clockwise, negative indicates counterclockwise, or lowercase l indicates counterclockwise. If you have equal amounts, that is called a racemic mixture. And if you have equal amounts, then the plane of polarized light does not move. It is just zero. So it does not rotate the plane of polarized light. You have a plus 20, you have a minus 20, and it's at zero again. So a racemic mixture is equal amounts of both optical isomers, and you put that in the polarimeter, and it reads zero. All right, the valence bond theory. All right, so we're going to look for the formation of this complex. And so this one is a coordination number equal to 6, and it's octahedral. Now we're going to look at our 5d orbitals. And we are going to split that in our crystal field theory. And 5 are not at the same energy. We have 3 of those orbitals at lower energy and 2 of those orbitals at higher energy. All right, so here are the 5d orbitals. You do not need to know how to draw them or even what they're called. dxy, dyz, dxz, the dz squared, the dx squared minus y squared. All right, so those are your 5d orbitals. We're just going to draw circles and put electrons in them. All right, and so when you have your 5 orbitals, they are going to be split into 3 at lower energy and 2 at higher energy. And you don't need to know, again, that you don't have to know the dxy, the dyz, the dxz, the dz squared. You just have to know that you have 3 orbitals on the bottom and 2 on the top. So you had your 5d orbitals. Now you have 3 at lower energy and 2 at higher energy, and this is only for octahedral. If you are not octahedral, then this is not the arrangement that you will get for your 5d orbitals. All right, so now we have to figure out the distance. So you have your 3 orbitals on bottom and your 2 orbitals on top. The energy difference here is called delta. All right, and so now we're going to have to figure out if we're going to put the electron in a higher electron orbital or if we're going to pair it up. All right, now if all of the electrons stay at the bottom first, so the first 3 will go in the same no matter what. So you put in 3. It is about where does that 4th one go? Does the 4th one, if we're in a straight chain, you put in 4 by putting in 1, 2, 3, and 4. Now they're not the same energy. So we're going to actually do both. If it is a low spin, then it stays low and it pairs up. We're also going to have some that are high spin. If it were a high spin, then the 4th electron would go up. So you would have your 1, 2, 3, and then the 4th one would go here. So this would be a high spin, and this would be a low spin. So in order to know where the 4th electron is going to go, you need to know if you have a high spin complex or a low spin complex. All right, again, right. So high spin or low spin. It's all going to be based on the delta, the amount of energy, the separation. So if you had your 3 and then the 2 were way up here, then you had this huge delta versus you have 3 here and 2 here, a very small delta. All right, and so here the energy, it would save energy to pair up. Here, electrons don't really like to be paired up, so if it sees an orbital of low energy, it will just go up here. So this is what it's going to look like for a low spin. And this is what it's going to look like for a high spin. All right, so again, if you have, let's say we have a D6, low spin, all 6 electrons down here. A high spin, you go 1, 2, 3, then the 4th one goes here, and then the 5th one goes here. Then you come back down and pair up. So this is a D6 low spin, and this is diamagnetic. All electrons are paired, and this is a high spin D6, which is, of course, a paramagnetic. And you have 4 unpaired electrons. All right, and so if you have 2 empty d orbitals up here, these have to be completely empty. If empty, then your electron configuration, or no, your hybrid orbital is going to be a D2 sp3, because it's going to take these 2 d orbitals and then go to the s and then go to the p3 for your hybridizations. If this is not empty, all right, so it has 1 or more electron in these 2, then it is going to be an sp3d2 for your hybridization of that complex. All right, so you're either going to have D2 sp3 or sp3d2, depending on if there are any electrons in those higher 2 orbitals. Now, in order to know if you're going to have high spin or low spin, when you have a weak field ligand, so if all of the ligands are weak field, then it is going to be high spin. If you have 1 or more strong field ligand, then it's going to be low spin. All right, it's going to be low spin because you're going to have a very large delta. All right, so this one has a small delta. So again, the small delta means that the separation of the 3 and the 2 are very, very small. All right, and so it's just going to go to the high spin. The 4th one's going to go up here, versus this one has a large delta. So that means your 3 orbitals are down here and your other 2 are way up here. And so it's going to be a low spin, stay down at the low energy orbitals when you have these ligands. All right, so you'll need to know your weak field ligands and your strong field ligands. Note that gas chambers, you have cyanide, and you also, that's your cyanide for the gas chambers back in the day, and of course carbon monoxide poisoning. So these are very strong ligands. They come on, they don't come off, they don't let oxygen in, and that's why they are used. All right, that is pretty much the end of this chapter. We will do some more stuff next week for the last test before the final.